Good morning. So we'll move on to two-phase sampling. Is it to that, to right, or it's okay? Okay. Yeah. Or you can maybe turn off one light, just one. Yeah. So that's probably no, that's right. Thank you. So so two-phase sampling is uh a very effective way of combining information and achieve the cost efficiency. And I personally think that two-phase sampling is really a promising area of research. And nowadays, especially in causal inference and active learning or whatever, these days, I think in machine learning context also, this two-phase sampling idea can be very useful. So I like to first emphasize that, and then move on. So we can use X variable to in the design, right? Especially if you can use X to do a stratification, or we can use X to employ unequal probability sampling, PPS sampling, something like that, which can improve the efficiency. So, or we can use X to improve estimation efficiency in the estimation stages. So basically, in either case, we need to the presumption is that X is available in the sampling frame. So now question is, what if X is not available, right? So we don't have a good information in the sampling frame, but we know that X is useful. Then idea is we can use two-phase sampling to compromise. So in phase one, we can use a very simple design because I don't have any information in the sampling frame. So I just do a very simple design, like simple the sampling, and observe X. And then after that, I treat A1 as a, so this is the population. And then I select A1, right? And measure X. And then I treat A1 as a population. And then from there, I can select a sample, A2, right? And observe Y. So X. So observe Y, but because A2 is a subset of A1, so that means I can actually also have X information available, right, in A2. So that is the basically the basic structure of two-phase sampling. And it is sometimes called the double sampling. And then it also has some connection with the missing data because you can think it as a, so A1 is the original sample, right? And then A2 is a set of respondent. You observe Y only for the respondent group, right? So that in that case, you can view it as a missing data problem as a two-phase sampling, although we don't know the mechanism for respondent response in general, right? But still, sometimes it's we create missingness by design. So then in that case, it is called planned missingness, right? So planned missingness is a feature of one important feature of two-phase sampling, let's say. We create missingness intentionally to reduce the cost. So why we are doing this? Because the measurement for Y is very expensive, could be. So like X is a health related information, right? from survey. Okay, so you can obtain measurement on the health related information from the survey. Then the cost is actually for the obtaining survey. But why could it be the actual medical exam, right? Like MRI. That could be really expensive, right? And then you cannot really take the rather than just doing a random sample and and apply MRI, we can actually use X to identify, right, risk group, and then use X to determine who are more eligible to get MRI measurement. So that is reasonable thing to do. Another example is that in the forestry or NRI, right? So X is the satellite image, information or remote sensing. You don't measure it directly. You just observe it, right, from outside. You just you obtain information, proxy information from a picture from a plane, taking picture from plane, and then use the picture to classify or have a rough estimate of the some information that you're interested in, like in the forestry, they are interested in some kind of a particular disease for trees, right? And then you cannot really get the information until direct measurement, visit and direct measure, right? But still, you can take a picture and get some rough information. So that could be useful, right? So that is basically the idea. Okay. So then we have a two inclusion property. One is the first order inclusion property on the first phase sampling, and then this is conditional inclusion property for the second phase sampling, given the first phase sampling. So the problem is that the overall first phase sampling on the two phase sampling is actually an expectation. So this is actually overall possible, right? So so what I'm interested in, here's a particular element, and I'm interested in the probability of obtaining this. So you could have many different possible, right? Possible A1. And so then it's difficult, right? Because you overall possible A1, you can evaluate. So if A1 particular A1 doesn't really include R, then this condition property will be 0. But there may be many different A1s that contains 1, but that contains I, right? So then conceptually, this is the definition, but you don't have many realization of A1, right? So you cannot really compute it from the data. So then, we'll worry about that later. But anyway, so the tricky part is that it has a dependency on A1, and so if that dependency disappear, then it is called the invariance. So invariance is a two-stage, right? Two-stage sampling. So in that case, data has a hierarchical structure. You have a cluster, and then cluster have, right? The population has a cluster, and cluster has many elements. So then element belongs to only one cluster. So then it really doesn't depends on other, right? Which clusters belongs to I mean selected or not doesn't really make any difference. So in that case, invariance holds, and then the inclusion property is easy to compute. So then if the invariance does not hold, so right, then you cannot compute the first or the inclusion property, and so we cannot really use Horvitz-Thompson estimator. So basically, this is the point is that in this example, for example, this is weight is random variable. Right? Because it even though the xi in the final population is fixed, okay, xi in the final population is fixed given, but the way which one we select is random, right? So then the denominator will be random. So r is fixed, xi is fixed, but this guy denominator is random. So the conditional probability will be random. So and then we don't know what is the expectation of this guy, right? So this is the pi I, but we don't know. We cannot really, unless we know, right? So this we don't know the expectation. So then what should we do? Well, the idea is give up Horvitz-Thompson, but still we can do something. So the idea is, okay, it's not really, so we suppose we have a what is the Horvitz-Thompson estimator on the phase one? So this is my Horvitz-Thompson estimator that I would use, right? If I had observed the yi in A1, then I would use this Horvitz-Thompson estimator. And this is unbiased. Of course, this is unbiased, right? Unbiased for y. That's no problem. The problem is that we cannot really compute it from two-phase sample, right? We cannot really compute this estimator, ideal Horvitz-Thompson estimator, from two-phase sampling because we don't observe yi in A1, right? We don't observe yi in A1. So then what should we do? Well, we treat this as a parameter. So this is not really an estimator. This is a parameter. Conditional, right? This is a parameter given A1. This is just a parameter. So we treat it parameter. So it's like this. So here's a U, here's a A1, right? So what I'm going to do is that I'm going to treat A1 as a population, right? And then I have a sampling, right? I have a sampling. And from A2, I observe Y. So I can basically use, I know the selection probability, right? So I can basically use A2 sample to estimate the quantity defined in A1, right? So that is basically the idea. Yeah. Okay. So then basically you can see that, okay. So that means your estimator given A1, right? So conditional expectation of Y star given A1 is equal to Y hat HT1, right? So conditional expectation of y star given A1 is equal to this one because we use a sampling twist. We just apply the Horvitz-Thompson estimation method, right? For this guy. And then after that, I can take expectation both sides with respect to A1, right? Sample design for A1. So I can take from here, I can take expectation with respect to A. Then expectation of y hat Horvitz-Thompson one, which is y. From here, we can do it. So that gives us an idea of how to show about this unbiasedness, right? But the variance, basically we'll do the same decomposition, right? Variance of the variance one of the expectation two and expectation one of the conditional variance, right? Start. So that is the usual decomposition. So then this guy is actually equal to this guy. And this guy, if you work out, you can check that this guy is equal to this. So that, conceptual level, this is okay. But it's not really clear at this point how it really means when we apply to our specific problem. So I'm gonna okay. So I'm gonna move on to more specific case, especially when use regression estimation. So this is the main part in today's class. So I will first start with a simple design. So simple design means that simple undersampling and simple undersampling. So this is I did say this is part one. And then later here, page 12, I will cover more general sampling design where we have a general sampling design, phase one and phase two. So part one is more beginning step to help our understanding. So okay, so if the sampling design is a simple undersampling in the first phase and simple undersampling in the second phase, then life is easy, right? That means that simple mean should be unbiased, right? Simple mean is unbiased to the population mean. So we can actually define that compute. So phase one, we observe xi in A1 so that we can compute x bar one from, so notation is sample size is n. So that means we have a, so that is the sample mean. Here, the phase one, we compute this one. Phase two, we compute x bar 2 and y bar 2. No, not n. We have a sample size r, right? So we have r. Just a simple mean, right?
I have a question here. So since in phase two, we select a simple random size of R, right, from A1. So we are taking the same X, the X is same in A1 and A2, because
I'm sorry?
in phase two, we are taking a simple random size of R, right?
Right,
And this sample is taken from phase one, right?
from A1, right,
Yes. So since X is common in phase one and phase two,
right,
and in phase two, we are taking the sample from phase one.
right.
So we are taking the same X, like
We are taking
the same X, the
same X, right, so X is the same.
same, but the repeated X, because X is also
Ah,
available.
okay. Well, okay. So we have a, suppose we have a X1 to X10. So this population n equal 10. Small n equal to 5. Suppose then we have a, say we have a, okay, R equal 2. So we have a sampling, we have 10 elements, we selected 5 at random.
Mhm.
And as, assume that suppose we happen to select the first 5.
Mhm.
And then we just, so basically this guy is the same as this guy.
Yeah, that is.
Right. Okay. So, so what I know is that the expected value of this guy will be conditionally unbiased to x bar 1, right? So then the idea is, okay, the idea is simple. In the regression estimator, the usual regression estimator is this. So this is the usual regression estimator where this is the population mean. This is a sample mean. The sample mean. Right? So this is the usual regression estimator. But in the two-phase sampling estimator, we don't know. We don't know population mean of X. So basically we treat A1 as a population and A2 is a sample, right? So in A1, we have a XI in A1. So this is the population. So then population mean is this guy. So this is the population mean. And then this is a population. And this is sample. So this is sample mean. This is population mean. Okay. So that's basically the idea. Then of course, this regression slope cannot be computed from the population, right? This can be computed from the sample. Okay. The main difference is that now in the usual regression estimator here, right? This guy is fixed. This x bar n is known, right? Fixed known. But now in the two-phase context, this is actually estimated one. This is a random variable. This is random. This is random. Everything is random. But the level of randomness is different, right? Because this guy is random but has more sample size than this one. Okay. So we actually two levels of randomness, right? So x bar subscript 1 means that we have a sample size n. So sample size n could be large, right? So usually n is much larger than r. So you can say that maybe this is about 10, I mean 1000, this is probably about 100, something like that. Okay, so if you understand this way, then basically this guy uses 1000 sample, this guy uses only 100 sample. So then you may use that information, extra information to do something better. Okay. And then what kind of property can we say? Well, first of all, when we want to compute the variance and things like that, what makes it difficult is that this guy is not linear, right? It's a product of two random variables. So that creates a nonlinearity, so which is not really pleasant. So the usual technique is that, okay, the usual technique is to face regression to face is this guy 2 plus x bar 1 minus x bar 2 theta hat 2, of course. I should have a subscript 2 to emphasize. So then usual technique is to consider the limit. What is the limit? So beta 2 should converge to something. So let's call this as a B. So let's do this way, right? So if you just add and subtract, you have something like this. So you are doing just this is kind of same technique we applied this technique before in the regression estimation. So once you do that, then this guy is linear. Linear, so because linear function of the random variables, right? The only random variable is x bar 1, x bar 2, y bar 2, something like that. So we basically made it as a linear function of the random variable. And this guy is of course nonlinear, but this guy converges to, this is usual, so converges to 0, right? And this guy is converged to 0. And it goes to 0, and then you multiply something also goes to 0. So then the product will goes to 0 faster than the others. So to be more rigorous, this is 1 over 2 and 1 over 2. Here the sample size R. This guy is 1 over 2R. So the product becomes you can actually have a faster, right? So the convergence order is root 2n order, 1 over root 2n order. But you multiply two terms that are 1 over 2n. So then the overall is 1 over 2n. So that basically, so that means you can say that the extra term is negligible, asymptotically. Small order. And then once you ignore this, we are happy, right? If you can kind of ignore this part, then we know how to compute the expectation and variance, all these. So, so if you take the expectation, for example, so this will converge to the expected value of x bar 1 is unbiased to x bar in the population. This is also unbiased for the expectation of x bar, right? So that means this guy will has a 0 expectation. And this guy is a y bar too. So that means it will converge to y bar. So this is approximately unbiased. To be more rigorous, let's call this as a uh, two-phase linearized. So then expected value of this linearized one is the expected value of, so we want to write it as a something like this, right? So if you write this way, so that means because you have two randomness, your expectation, take the expectation with respect to the first phase, the expectation for the second phase. Then what is this? So let's write it down. Right? So if you write this way, then you can take expectation inside. So then the expectation of this guy will be y bar 1. Expectation of this guy is just, this is constant, fixed. This is not random, conditionally, right? So this is fixed. And this guy is expectation, should have arrow this way. Expectation will be x bar 1. So it's the expected value of x bar 2 is x bar 1. So x bar 1 is equal to 0. And so you get which is y bar. Okay. So that means it is unbiased, regardless of what the limit is, right? And variance. So we can do the same thing, but maybe we need we can use the extra. Okay, so now we are interested in showing this. So what is the variance? So we are interested in variance of L, right? So that is the variance of expectation of variance of where y bar L is y bar 2 plus x bar 1 minus x bar 2 prime B. Okay. Okay. So the first term, we already actually we already computed the what's inside, right? So the inside what's inside is y bar 1. So that is yeah. If you am I correct or not? If you take the expectation, right? Right? If you take the expectation with respect to second phase, then you get this. So then this is true. You cannot really simplify it further. The second one is you want to compute the expectation of 1 and conditional variance. So what is the conditional variance? So you basically, this is the variance over y bar 2 minus x bar 2 prime b conditional on A1. So you can write it. So if you define right? If you call this EI, this is just the mean of the EIs in the second phase. So that means this is why we do that? Why? Because this is a simple sampling. So so we are basically interested in computing the EBA2 given A1. So that means the sampling is a simple sampling of size R from N. So that is you have this guy. And then you have something like this. Minus E bar square. So you can call it as E square. So here, yeah, so actually the summation is not really accurate. Let me write it again more rigorously. So 1 over R right? This is because we condition on A1, this is the population. So this is the variance of EIs in A1. So then R and N is all fixed. So the expectation of, so this is a sample, right? Sample S squared. So then this sample S squared, expected value of the sample S squared on the simple sampling is a population S squared. So then this is actually population. Now you can have a population S squared. So that means this guy is a population, right? So to be more rigorous, we can also write it. So if you do that, actually, so 1 plus 2. So this guy is you can write it as a p prime sx square p plus s e square. So that is some kind of total sum of square is a regression sum of square plus error sum of square. So we want to, so basically this guy is s e square, right? So we want to simplify. So then you end up getting something like this. Plus capital N S E square. That is the algebra. So actually here you have S square both sides, and so then you have some 1 over R minus 1 over N plus 1 over N minus 1 over capital N. So there's some cancellation. So this is the total. And interesting part is that total variance has a two component. One is the component that is explained by x, and the other one is the component that is not explained by x, right? And the part that is explained by x has a sample size n, small n. While the part that is not explained by x has a sample size r. Which makes sense because we want to leverage it, right? So the whole idea is leverage x, leverage this guy, right? If we don't use it, right, we just use this one, right? But because we use this, we want to gain something. The efficiency gain is that we actually, so the leverage, this is the amount of leverage that we achieve by using x bar 1 instead of x bar 2. Okay. So that is basically the idea. So that is basically the point. So you, by using regression estimator, you gain something. So remember, so this is, you have two things, right? Y bar 2 plus, so if you know population mean, you would use this one, right? So this is the idea, maybe idea. But in reality, we don't know. Right? You don't know this. So you cannot really leverage. You cannot use the population total of X to use X as an external control. You cannot do that because you don't know that. So what should we do? We have two choices. One is, okay, use X bar hat as X bar 1. So that is one first choice, which is a two-phase regression estimator. Right? So that means you use the first phase sample mean of X to leverage. The other option would be do nothing, right? So that means you just use the current sample. So if you plug in, if you just use this one, then right? If you just use this one to over here, then second term is 0. So you are not really doing any gain, right? So that means you just use it y bar 2. Simple estimator, do nothing. So use direct estimator. So then this gain is this amount. Okay. So that means what? The gain, so this is greater than 0, that means this is better, right? So the gain is high if this guy, this is the regression sum of square part, right? So the contribution to regression is high, then this gain is high. Also, if R is much smaller than N, right? That means you leverage a lot, right? You leverage a lot. That means if N is much larger than R, relatively speaking, then your gain will be high. Okay. And then next topic is that how to choose N and R. So C0, C1, C2 are known. So they are given. I know how much it costs for each measurement. But what I don't know is that given the budget, what is the best sample size for say phase one and phase two. So this is a very practical problem, right? If you think about that, if you are in a company and doing companies care about money, right? They like to they hire you and to pay you, maybe you guys can make a lot of money, but you should show some benefit, right? For paying you, right? And then the one of the gain is probably one of the big chance would be you can actually do some simple mathematics and come up with some good plan for this kind of a result. Then your boss will be happy. Okay, so here's so how to, right? And then if you yeah, I'm just kidding. If you get a raise, then you can donate to Iowa State. So anyway, so okay, how to solve this? So this is not so the plan strategy is okay. Let's write R as a nu times n, and then nu is what? Second phase sampling rate, right? So let's first, so this is new start actually. So let's first find the optimal sampling rate first, given n. And then once you, okay, so once you know that, that means what? You can actually, so this is the step one. Second step is C is given. If you know this one, right? And then you now in a position to so this is known. This is known. This guy is here. So then this is just a linear, right? Equation for n. So you can actually obtain n star. Then you are done, right? So you can first compute this guy and then compute this guy. So second step is easy. The first step is a little bit more tricky. So basically we want to get rid of n first to do something. So okay. So variance. So what is the variance? 1 over R. Let's forget about. So if you remember, if you check this formula, right? This is the formula that we're going to use. So the variance formula, if you look at the variance formula, let's forget about this finite comparison question because capital N is like 10 million something, right? It's very small anyway. So let's forget about this. Then all basically your you have a two component, 1 over n b prime s x x b prime plus 1 over r s 1 over r s e squared. Oops. Oops. Not b prime. Oops. Plus. And then you can even use the, r square. You're going to use the r square. So if you use r square, that means you can actually r square. Right? You can use r square to express this component. Okay, and then minimize V subject to C equal C0 plus, okay, C plus C1 n plus C2 n nu equal constant. Means that because this is constant, this is also constant, so you can remove it. If you subtract, this is also constant. And so then basically you can write it 3 times C1 n plus C2 n nu subject to C1 n plus C2 n nu is constant. Why? Why? Because this is constant, right? Because this is constant. Multiplying the constant to the object function does not make any difference. So under the constraint, right? Under this constraint, this is constant, right? So then it's okay. Then why we are doing this? Well, because if you do that, then you have actually very interesting. You can basically cancel out. Okay. Well, you can even actually move. Sorry, you can even move as y square, and then you only have r square plus 1 over nu. Uh, times c, this guy. Okay, here's a magic. So the magic is you actually have everything. N goes away. N goes away. Okay. So previously we had two, right? N is unknown and nu is unknown. But if you do this trick, then you have only one thing unknown, right? Which is nu. So then you can actually, this part is a linear in nu. This part is a linear in 1 over nu. So that means you can actually further simplify to something like, so this, sy square 1 over r square divided by nu plus c1, and then c2 sy square r square nu. So you have a nu in 2 places. Everything else is just constant. So you end of the day, what you are going to solve is just this guy. A and B positive. So you want to minimize this guy. So end of the day, what you want to solve is just this problem. A divided by nu plus B times nu. And we want to minimize this one with respect to nu. Okay, that is not really difficult because we can use some kind of a simple, inequality, right? So we know that, and that is that the lower bound doesn't depend on nu, right? And so that means you can actually know that whenever you achieve the lower bound, that is the minimizer. I mean, right? Minimize. That guy is the minimizer. So then that means all you have to do is to solve this equation. Right? So the minimum occurs when you have this equality. So that means the minimum occurs when B. Square root of A divided by B is the answer. Okay, so that means this is okay. We are almost finished. This is oops. This is A, right? This is B. So this is A, this is B, and all you have to do is compute the A divided by B and take the square root. So A divided by B, and then you can cancel SY squared. And then C1 divided by C2 times I minus R squared divided by R squared, which is this solution. We are done. Of course, the statistical interpretation which should follow, right? This just what I just proved is a mathematics area, but we, as a statistician, we need to give a statistical interpretation, and which makes sense because if C1 is high, we should select more second phase. So, right? Because the idea is to reduce the cost. So if this is expensive, that means we should give a higher. So also another way is if R square is large, if R square is close to 1, that means what? That means you don't really need a lot of Y to leverage a lot of sample size in second phase to leverage because X is enough. X is pretty good, right? If X is pretty good, then it makes sense to sample more X's to leverage more than training. So R1 is the sample size for training, and N is the sample size for leveraging, right? So then there's some kind of a trade-off. Okay. So that's the main theory. And now I'm gonna move on to generalization. So we have basically we have that means we have a inclusion probability. First phase is inclusion probability, second phase inclusion probability. So it looks complicated, but it's not difficult. I mean, we should not be confused between complicated and difficult, right? It's just complicated, not difficult. You may think that complicated thing is difficult, but no, that is not, right? Usually, you just don't want to be involved in the complicated thing, and then you want to believe that it is difficult, but that is not. So it's very hard to deceive yourself because you don't want to do it. But if you really want to understand it, then you should see the reality directly and then try to what is really difficult and what is not. So this is okay. This is not difficult. It's just complicated. And also, I mean, we covered a lot of methods enough to understand. This is just the notation, right? This is just because we have two steps. So I mean, two phase. So that means we need to introduce two different notation, right? But the concept itself is the same. Okay, so this is the prediction part, and this is the error part, right? And we want to use the second phase sampling rate. And simplification is that, okay. So if it's complicated, we try to be simplified. And one way is to make the simpler notation. So I don't know whether this is simpler, but a little bit simpler. And just once you write this way, you kind of understand that this is indeed meaning this one. But okay. Anyway, we can apply the same idea and see that we can, okay, the uncertainty in beta hat can be negligible, right? Using the same trick. Now, that means you have actually flexibility, right? So what that means? What that means? So this means that you have a flexibility. You can choose different beta hats. And then that means that you can actually be more, innovative or at least try to seek some convenience. So one choice is just this one. And then that means what? If you choose this one, that means you are actually equal to 0, right? So this is just a different way of writing. So this is a closed form solution, but this is indeed the Ismaili equation that solves the beta hat. And that means if this holds, that means you can actually multiply, pre-multiply, right? Lambda, both sides. Okay. To get and use it. Because this is an equation, you can apply. That means the equation leads to take this, can be written as this group. So that means we have this. So that means we have a second term is equal to 0. So this one is a prediction. This is a bias correction, right? So prediction depends on beta hat, right? Prediction means that you depends on how you want to predict, right? So you can come up with many different, predictors, and you can predict. But as long as you can do bias correction, that means you can always recover, right? Correct the bias of your particular prediction estimator. So your particular prediction estimator can be bias corrected using the second term, right? That's why we say that this is unbiased regardless of the choice of beta hat. Although the efficiency, right? Efficiency matters, because if you choose different beta hat, then the variance could be different, right? The variance could be different, but the bias is unbiased, no matter what beta hat you use. Okay. So one observation is that, okay, here's a condition that makes the bias correction term asymptotically negligible. I mean, algebraically equal to 0, not asymptotically. So if you include x to contain the 1 over pi, so this is actually sometimes called internal bias calibration. In the prediction, right? So the concept is that, okay, what condition should we impose in order to my prediction estimator to be biased, I mean unbiased, asymptotically unbiased. So that that condition, that kind of condition is called internal bias calibration. You bias corrected externally, right? So this is a external way of bias correction. This one with this condition is an internal way of doing bias correction. Okay. And then Taylor expansion. So if you do the usual Taylor expansion, right? So the only thing is that beta hat. So think about conceptually, what is the conceptual, limit of beta hat that is negligible. So this part is actually the same as, beta hat minus beta star times x hat here. I'd say x hat 2 minus x hat 1, something like that. What minus. But anyway, this guy is 1 over root 2n. This guy is usually 1 over root 2n times this is total. So we have n. So times and times, and then we have, so should have a p because they are random variable. So that means, anyway, this is the main term. And then this is linear, right? So this is actually sometimes called the influence function. So this is actually a function of a vector. But if they are IID, that means this is IID. Okay. So once you linearize, we are in a position to compute the variance, right? Mean and variance. So design unbiased is easy because if you take the expectation, with respect to delta, then this guy cancels with this guy, right? And then this guy cancels, and this guy cancels, and then this is just the Hurwitz Thompson estimator. So then you take the expectation again for sample A, then you can unbiased, design unbiased. The same thing. The variance, we are doing we can do the same thing, right? Variance of the conditional expectation A1 plus expectation of the conditional variance. So this part, we already seen this. Right? Just to explain. And the second part is you can basically, so conditional on A1, the only random variable is delta. Okay. So that means you need to worry about the conditional, covariance of this. This is a summation, right? So if you view it as a summation with respect to delta, then you have something like this. Okay. And then interesting part is that, okay, if you care about pi, determining pi to I, so pi to I1. So this is basically, you don't really have a control on first phase sampling. So first phase sampling is mostly just the simple random sampling, okay? But second phase sampling, you want to do something better than simple random sampling. And then you care about a second phase sampling. That means you want to do something. So, okay, let's make life easy and suppose that I want to do Poisson sampling. So if you do Poisson sampling, then this is independent, right? So then you actually can simplify. So double summation becomes a single summation, right? Because of independence. And then the only thing is that you only have worry to about I equal to j. So if I equal to j, then this one is a square, and then this one is pi I times, right? So this is delta I, delta j is more like a pi I 1 minus pi I of 0, right? So if I equal to j, if I equal to j, then you have a covariance, which is actually you need a 2, subscript 2, but so that means there's actually I have a typo. So it should have a 1 over pi 2i given 1, 2j given 1, right? Because see, I have this one. I have this one, right? So here we have a weight, this weight, and this weight. So sorry, there's a mistake. So there's a type I should include. But the answer is correct. So if you do that, then you only worry about the I equal to j, right? Then you can get basically pi I 1 minus pi I divided by pi I squared. So then you get this. Okay. I think I'm almost done for today. So then basically you want to minimize this. So you want to find the way, minimizing this one, right? I mean, you want to find the pi ij, minimize this. So the constraint that you might want to use is this one. So given under the Poisson sampling, the sample size is, the expected sample size is 1R. So this is the constraint. So minimize this one, right? Minimize this one, subject to this constraint. You can use Cauchy-Schwarz inequality, right? To obtain this one. Okay. So that is actually, and then if xi is a part of, I mean, the first order inclusion property is weight is a part of the xi, then this k is just the constant, so you can go outside. So you get this one as the optimal weight. And this is actually very promising, research technique. And I think that this nowadays in machine learning area, they have a lot of investigation of this related topic. And so I think whoever you are interested, some of you are interested, you can take a look at this paper and figure out. I'll be happy to discuss. So I think that's all. I will continue the other topics this Thursday.